That's what I did last time. And today, we're going to continue with that, right? Now that we have our rules for derivatives, I don't need to do the limit definition now, right? I don't need to do the limit definition now. I have shortcuts for specific cases, right? Number one is one of those specific cases. It has the addition and subtraction rule of derivatives, right? And it has the power rule. So we just go ahead and, if I'm looking for the derivative of this, that's what dy dx represents, by the way. It's the derivative of your y function with respect to x. Sometimes I write it as dy dx, sometimes I write it as y prime. Both of those things mean the same thing, right? So it's up to you if you want to write this as dy dx or if you want to write it as y prime. Both are acceptable as a form of a derivative. So then I can say this guy right here is going to come out to be 6x squared, right? Plus minus 8x plus 7. And then, of course, the derivative of a constant of that 16 is just going to become a 0, right? The derivative of a constant is just 0. And that's it, guys. That's your derivative, right? Gone are the days of having to write down the limit definition and foiling out x cubed, right? X plus h cubed, x plus h squared, and foiling those guys out and canceling out those like terms. Can you explain really quick? Of course. So what I'm doing here when I'm calculating the derivative is I'm taking each of these guys and looking at them individually because these guys are being separated by pluses and minuses, right, Brandon? And last section, I found out that you can take the derivative of each function that is separated by pluses and minuses. So I can just focus solely on this function right here and take the derivative of that on its own. And what I can do there is look at the coefficient rule combined with the power rule. The power rule here states that the derivative of x cubed is going to work out to be 3x squared. 3x squared. And again, if you don't remember the power rule, if I have x to any power, the derivative of that with respect to x is going to equal to n times x to the n minus 1 power. Right? So that's where that 3x squared comes from, and the 2 is just the coefficient that comes along with it. And we found out if you take the derivative of something that has a coefficient, like if I had a k times a function, and I was taking the derivative of this guy with respect to x, that's just going to equal to k times the derivative of whatever f of x is, right? In this case, f of x is x cubed. The derivative of that is 3x squared. So I just multiply the coefficient with that, and I get 2 times 3 times x to the second, and that's how we got 6x squared. And then you're going to do that for each of these functions that are being separated by pluses and minuses. Yes. I was like, 4 parentheses 2x. Yes, you're right, Brandon. 4 would be the coefficient for this one, times the derivative of x squared, which is 2x, and that's how we get 8x right there. Okay? And last but not least is the 7x, which would be 7 times the derivative of x. This is the part where some people have a little bit of trouble. If it's x by itself, it's actually 1x to the 0 power, right? Because the coefficient for this is a invisible 1, right? It's an invisible 1. So you bring down that 1, and then x to the 0 power is just 1. So that's why you end up with just a plus 7. And then, of course, the last one, the derivative of 16 is just 0. Okay? And that's that one, Brandon. Hopefully that answered your question for that one right there. All right. With that, we're going to go ahead and move on to number 2. Number 2 is asking me to evaluate this limit, right? Evaluate this limit as h approaches 0. Let me leave this on the screen just in case some of you guys are writing there. And you could try to evaluate this one. You could try direct substitution, which it won't work because you get something over 0. Actually, you get 0 over 0, which then leads to something that's undefined. So you have to try to simplify it. And one method that you could do to simplify this is expanding the binomial in there of x plus h to the 5th power. So you could rewrite this as the limit as h approaches 0 of, you ready? If you expanded that out, that would be x to the 5th plus, oh God, I don't remember the coefficients for x to the 5th. Let's see here, it'd be like 1, 1, 2, that's to the 1st power, that's the 2nd power, that's to the 3rd power, that's to the 4th power, and that's to the 5th power. Oh God, that's just horrible. Why would someone bother to FOIL this out. This is going to come out to be x to the fifth plus 5x to the fourth h plus 10x to the third h to the second. Oh God, that's just horrible. Why would you even bother expanding this whole thing out when I told you guys, if you can identify what this represents, right? What this represents. This right here represents a limit definition of a derivative. Does it not? Hopefully you can see that. It's the limit definition of a derivative. And since it's the limit definition of a derivative, if I can find out what the original function is, I can probably use my shortcuts to calculate the derivative instead of doing this horrible expansion. By the way, if you don't recognize this, this is called Pascal's triangle, and it helps you figure out the coefficients of binomial expansions. And I was already like, that's considered a shortcut back in algebra 2. And I don't want to do that. That's a horrible shortcut. I have a better shortcut here. If I see that this is the limit definition of a derivative where the function is equal to, and you can identify what the original function is, by the way, if you look at this, the original function, I hope you guys can see it, it's going to be x to the fifth. Once I know that the original function is x to the fifth, I can just use my power rule, right? And I see that the derivative of this guy, the derivative of this function, is just equal to 5x to the fourth. And that right there is what this limit would be evaluated to. It will be evaluated to 5x to the fourth. And you don't have to do all this stuff and then cancel out your x's anymore. You just need to be able to identify that that's what it is. And if you can't identify it, bam, you've got your answer without having to do all the work that you did back in the first section of this chapter that hopefully you guys have already done the homework and completed those problems. By the way, if you haven't and you go back there to do those problems, I still expect you to do it using the limit definition, even though you know the shortcut for it now. Okay? So for 2.1 homework, if you haven't done so already, do not use the shortcuts for them. I want them done using the limit definition. If you're in 2.2 doing the worksheet homework, you're allowed to do the shortcut for them, and you can do it this way. All right. That being said, I saw a couple people join. I just want to double check with attendance one more time, making sure that if you are here, just type something in the chat just to make sure that I got you. Oh, it looks like a couple more people have joined. So I'm just only missing Jackie, Sydney, and Kimberly. If you guys are here, please type something in the chat. That way I can check you off that you are here. But that's the only people I have missing now is just those 3 people. Okay, let's keep going to today's lesson. I don't know if you, I didn't have this title up here. If you guys like writing down your titles, here's the title for today. Derivatives of trig functions. Derivatives of trig functions, right? You guys know what a trig function is, right? Sine and cosine, right? Those are one of the few trig functions, right? Today I want to talk about the derivative of them, right? Because you notice sine of x, we can't use the power rule. There's no power there, right? Just for the sine function itself. Now, if sine had a power on it, maybe we could take the derivative of that, but then you still have to worry about what is the derivative of sine itself, okay? So before we do this, and before we actually work into it, what I want to do is show you guys a graph of sine of x, and then let's talk about what do you think the derivative might look like? What do you think the derivative might look like? So let's go ahead and open up your graph, and here is a graph of sine of x, right? Starts at 0, goes up to 1 at pi over 2, and then it goes down to 0 at pi, and then, oh, I can move this. Cool. And then it goes to 0, goes down to -1 at 3 pi over 2, and then it goes up to back to 0 at 2 pi. Interesting, I can't go to 2 pi, but I can move it over here. So remember, what do you think of when you hear the word derivative? And I'm hoping that what you think in your mind when you hear the word derivative is slope of a tangent line, right? That's what you need to be able to picture when you see a function and you're asked, what's its derivative? Well, what's the slope of the tangent line of that function, right? And you'll say, well, which tangent line are you talking about? And I'm going to say, yes, all of them, right? All of them. Just not at the same time, right? But the derivative function is a function that tells you the slope of the tangent line at any given anchor point, at any given x, right? So this blue line will represent my anchor point here and my tangent point, right? And I can move it along here. And it's, as you can see, the purple dotted line there represents my tangent line, right? And what the derivative would look like, right? Or what the derivative is just the slope of that purple line, right? So the derivative at pi over 2 of sine, right? The derivative should have a value of 0 because the slope of that tangent line is 0. My apologies right now. I don't know why I'm speaking with a stutter or like a speech impediment right now, but it's bothering me a little bit. Hopefully it's not bothering you guys as much. Or now that I've pointed out, maybe you'll hear it and it will bother you. So I apologize again. So anyways, back to this, right? The tangent line right here is 0, meaning the derivative would have a value of 0. Whereas the tangent line just to the left of that point, just to the left, just right here, you can see that it has a positive slope, right? A positive slope, meaning the derivative value around here would be positive, and then it would go to 0, right? So it's positive from here to here, and then it reaches 0. And then what happens? It has a slope that is negative because you can see that right there. It's decreasing now. And since it's decreasing, my slope is going down. The change in the y value is going down and to the right. So it should be negative from here to here, all the way until this point right here where it reaches back to 0, right? Where it reaches back to 0. So right here it is flat, and then it is negative, and then it's back to flat, and then it's back to being positive again. And if you're looking at a sine function, it kind of repeats that everywhere it goes. The tangent line is just 0 here, and then negative, and then 0, and then positive, and then 0, and then negative. What does that look like? Well, I'm going to go ahead and turn off these dots here. I'm going to screenshot that, and I want to be able to draw on this. So give me 1 second. Give me 1 second. And if you got an idea, you can type into the chat right now if you have a general idea of where I'm going with this. And if not, just pay attention for a little bit, right? My sine function, I'm going to go over to the side over here. Paste this on here. Absolute value? Not quite, but that's a good guess. That's a good guess because absolute value does look like it has that V shape. But once it gets past the V shape, it goes off forever in the left and the right-hand side, right? Whereas this one seems to be going up and down, right? It seems to be going up and down. Yeah. So it doesn't actually go up forever. It actually goes up to, like let's say here, if I was drawing my tangent line right here, right there, it has a derivative. It looks like that's a positive slope, right? It looks like it's positive. So it's like somewhere up here, right? And then if I have my tangent line right here, my derivative there looks like it's somewhere right here at 0 because it's a flat horizontal tangent line. So the slope of that tangent line is 0, right? And then, so that actually happens a few times. That happens here, right? Because that has a tangent line that is horizontal, so it's 0 there. It also happens here, doesn't it? It also happens here. And up here, doesn't it? So there's a bunch of spots, there's a bunch of dots that I can see that the derivative value is equal to 0 because the tangent line at those points are equal to 0, right? But it also has these spots where they're positive, right? And it looks like it's the same slope. You see the slope right here at 2 pi and the slope right here at 0? It looks like they have the same slope. I'm just going to draw it in a positive sense. I don't actually know if it's right there or not. I know that it's in a positive value because the slope is increasing, right? And David's going, could it be cosine? Could it be cosine? Does it look like it's cosine? Let's actually double check one more time right here and see what is the slope at pi. And that's a negative slope right there, isn't it? It's somewhere down here. And David's going, it kind of looks like cosine. Well, cosine starts at 1, right, when x is equal to 0, and then works its way down, and then it comes back up. This is just me crudely connecting the dots, right? I don't know if they actually curve like that, but I do know that if I connect the dots, that kind of looks like cosine of x. It kind of looks like cosine of x, right? Because the slope here is decreasing right here as well, so it's going to be negative down here. And it actually continues over here as well, doesn't it? And it follows this pattern, right? You go over here, the tangent line over here was also 0. So that would be right here. And it works its way back to 0. And I think it just repeats itself, right? Because sine repeats itself. So the tangent line should repeat itself as you go from left to right on this thing. And David, I think you're right. I think it might be cosine. I think it might be cosine. So let's take a look here. This right here, Oops, no, that gave it away. Oh, shh, go away. No, okay. So pretend that didn't happen. So here's my dot, right? And here is my tangent line, right? Here's my tangent line. So you can see it going all the way across here, right? It works all the way over here. It works all the way over there, right? And I can actually tell Desmos here to graph the value of this slope, right? Graph the value of this slope. I'm going to have to do it right here. So that red dot, I don't know if you guys can see it. This red dot right here represents the slope of this purple line. So when this purple line is right here, you see the slope is equal to 0. So the red dot is 0 right there. And when it's over here, the slope is negative. So is the red dot, because the value of the slope is what that red dot represents. Okay, the value of the slope of that tangent line, the derivative, right, is right there. So as I work it through, right, you can see the value of it following along. So it's 0 here. And when I say it's 0, I'm saying the y value of it is 0. You see that? I missed. Can you like get to, hello? Can you get to 0? Well, you get the idea. It's negative and then positive. So it is 0, like right there. Man, why can I not hit you at 0? It doesn't matter. Okay, so when I have this thing run its course through, you can see, right, that it seems to be going down, and then it goes back to 0, then it goes back up, and it goes back down again. And I think you're right, David. I believe if I were to graph it, and I can because this is Desmos, here's the graph of the derivative. Here's the graph of the derivative. And it's this blue line that works its way up and down, and that's all it is. The derivative of sine, right, when you measure out those tangent lines and you work along the sine function, it just comes out to be equal to the cosine function, right? It just comes out to equal to the cosine function. So if I was asked to calculate, right, hey, if my function is sine of x, the derivative of that said function is going to equal to cosine of x. Okay? Now, there's a proof of this, and I kind of want to show you the proof. For right now, though, can you just write this down? Write it down somewhere that if you have a function is equal to sine of x, the derivative of sine of x is equal to cosine of x, right? Just write that down somewhere. But I want to prove that to you. I want to show you the work of this. This next part, you can write it down for your own sake, but you do not need to memorize it. It's just me showing you algebraically, because we just saw it graphically. I want to show you algebraically, how does the derivative of sine of x equal to cosine of x? Okay? So remember, what we've learned about the derivative function so far is that we only have to do it algebraically, the limit definition, right? The limit definition as h approaches 0 of f of x plus h minus f of x over h, right? That's the limit definition of it. F of x plus h minus f of x all over h, right? Now, get out of the way. So if I was going ahead and calculating this, and my f of x is this sine x function, I'm saying I'm looking for the limit as h approaches 0, right, of sine of x plus h minus sine of x all over h. Now, in order for us to do this calculation, in order for us to break down this thing right here, it takes a little bit of IM3 / pre-calc, right? I don't know if it's taught. I don't think angle sums is taught anymore in IM3, but it might have been taught to you if you remember it. It was like the sine of a plus b. You can split them up into trig functions that are multiplying with each other. So I can rewrite this right here. This sine of x plus h, if you look that up as the angle sum of sine, you can actually split this up. So I can write this down as the limit as h approaches 0 of sine of x, right, times cosine of h plus sine of h. What the? Plus sine of h times cosine of x. Okay? Again, how are you supposed to know this? It's stuff that you've learned in the past, and if you didn't learn it in the past, don't worry about it too much. This is something you could just look up. It's not something that's super mandatory. It's not something that is required for you to do the calculus portion. This is all stuff from before calculus. And if you don't have it in your repertoire, don't worry. You just if you come across functions that you don't know what they could equal to, for our sake, you could always look it up. I'm telling you right now, if you are interested in this, go look up angle sums properties, right? Go look up angle sums properties. So that's what that is, minus sine of x, right? And this is, of course, all still being divided by h. Okay. Now this next part requires a little bit more algebra as well. So let's go ahead and combine certain things together. So what I'm going to do right here is I'm going to see, hey, I have a sine x here, and I also have a sine x over here, right? I'm going to write that without the parentheses just so I can show you that this sine x right here looks a lot like that sine x right there because they are the same. So what I'm going to be doing is I'm going to be grouping this term and this term together and factoring out a common sine of x, right? Factoring out a common sine of x. So I can group those together and factor out sine of x, and then leave behind, right? Leave behind a cosine of h minus 1, because if I factor out the sine of x, there's only 1 left behind, right? And then I didn't factor out a sine of h over here because that's not the same as sine of x, so that's just going to be added along to the side over here, which is sine of h times cosine of x. And this is all, of course, being divided by h still, right? This is all being divided by h still, right? Again, if you're getting lost along the way, don't worry. I'm not going to ask you about doing this calculation by hand. I just want to show you that the derivative of sine doesn't just magically equal to cosine just because I show you a graph, right? I want to show you algebraically how it works out. So check this out. This is, if you look at this, right, this is one fraction right here, right? One fraction with a common denominator of h. I can split these up into two fractions, okay? I'm going to split this up into two fractions. I can take this right here and rewrite this as one single fraction itself, sine of x times cosine of h minus 1 divided by h plus sine of x, sine of h cosine of x divided that by h. And again, why am I doing this? Back in the limits section, right? Back in the limits section, there was a special limit, and one of those special limits was the limit as x approaches 0 of sine of x divided by x. Right? And you say, you're not looking at x's though. You're not looking at the limit as x goes to 0. You're looking at the limit as h goes to 0. Well, that still applies, right? If h is going to 0 and I'm taking the limit as h goes to 0 of this thing I just boxed in blue, if you go back and look at that, right, this thing actually approaches 1. This thing actually approaches 1. And if you don't believe me, you could type it in there, the function itself, sine of x over x, right? And let me go ahead and open. Wow, you're still playing? Just yeah, I'll just leave you going. That shouldn't cause any problem. So let's go to Desmos real quick here, and let me show you sine of x over x, graphically speaking, if you don't remember, sine of x over x, right? The limit as x approaches 0, right? It's undefined right here. The function itself is undefined at 0, but the limit exists, right? And the limit looks like it's approaching 1 from both sides. Looks like it's approaching 1 from both sides. So this right here is going to equal to 1. This right here is the other function as h approaches 0. What does that approach? And again, that's from the chapter 1 part of this. And if I go ahead and type that in, it's going to be cosine of x minus 1. Wait, was it cosine of x minus 1? Wait, no. What? Cosine. Yeah, cosine of x minus 1. There we go. There's that graph, whatever that looks like. But again, what does that look like it's approaching as x approaches 0, or in this case, h approaches 0, right? It's undefined here, but it's a removable discontinuity, which means the limit there exists, right? The limit there exists, and the limit from the left-hand side and the limit from the right-hand side looks like it's approaching 0. See that? Looks like it's approaching 0. So I would go back to my notes here. This thing right here looks like it's approaching 0 as I evaluate this limit. And those are the only places that have h's, right? So if I can evaluate those limits that way, I actually get rid of my h's. And this is actually going to come out to be now, once you simplify this out, sine of x, right? Sine of x times 0, because that's what the limit as h approaches 0 becomes, plus this guy right here is just 1, right? Because the limit as sine of h over h as h approaches 0 is going to be equal to 1 times cosine of x, Well, sine of x times 0, that's just 0. 1 times cosine, that's just cosine of x. And that's what the derivative is equal to if you were trying to derive this using the limit definition of a derivative. Now, do you need to know this to do derivatives of trig functions? Not really. It's important to see where it comes from. It's important to see graphically how this works. But if you're doing a problem and I ask you to calculate, hey, here's sine of x, give me the derivative of sine of x, you just need to tell me it's cosine of x. So if you're one of those people who like memorizing things off of flashcards, one side of the flashcard is sine of x, the derivative of sine of x is cosine of x. If you have that memorized, you're good to go. You're good to go. I just want to show you this because I think it's important to understand where this stuff comes from. And if it doesn't make sense to you right now, but you decide to continue on your math career, that's perfectly fine. This will come back to you, and it'll make sense like maybe 3 or 4 years down the line. But for right now, all I really care about for this class is that you understand that you have sine of x. The derivative of sine of x is cosine of x. Okay? The derivative of sine of x is cosine of x. I know that sounded like a long-winded explanation, but it is important. I do need to show you that, right? Anyways, let's keep going here. So, the derivative of sine of x, cosine of x. I have enough space like that. There we go. Okay, so let's move on. Let's go on to the next one down here. Get out of the way. Get out of the way. There we go. So, what about y is equal to cosine of x? And what about y is equal to cosine of x? And that one is a little bit different, right? That one's a little bit different. I'm not going to do the breakdown for that one, but I do want to show it to you graphically. So let's go ahead and graph cosine of x and see what its derivative looks like if I was looking for that as cosine is my trig function. And there's cosine as my trig function, and I have the answer kind of graphed there, and you can kind of see it, right? Yeah, right? So let's double check. We can see which function is what. So here's the cosine function, right? Here's the cosine function in red now. Okay, and at the very start of it, it looks like it has a slope of 0. And then when I go over here, my slope is negative. It goes down, and then it goes back to 0. And then it goes to positive. Then it goes back to here. And hopefully you guys can see that function, right? That derivative function looks like this blue line right here. And some of you guys might be able to identify it, and you'll say, that looks like sine. You're close. You're close. Sine. This sine wave does look like this, right? Except it goes up and then down. This one is actually at 0. It's going down and then up. So it's actually, that's right, Brian, negative sine. Negative sine. Very good. So the derivative of this, y prime of cosine, is going to be negative sine of x. So that's another one that I need you to put into your repertoire that you have to remember somewhere down the line so you can see, what it is and how to find it. Okay? Now that you know what's the derivative of sine and cosine, let's actually do some problems so you can feel like, okay, this isn't as bad as it looks. And I hope that's what you feel like once we actually get into this, right? So let's see here. I was looking for let's say I had an example here. I was asked to find y prime, or the derivative of y, given y is equal to x squared times sine x. X squared times sine x. Now, I know immediately right off the bat, you guys might want to write down, oh, I know this. Derivative of sine x, you guys told me, it's cosine of x, and derivative of x squared is 2x. This is not the derivative of y. Just giving you that heads up. Yes, the derivative of x squared is 2x. That is right. The derivative of sine x is cosine x. But the derivative of y is not those two multiplied together. That is not the case, right? Remember, we learned a bunch of rules here. The only one rule where you can do that if it's addition or subtraction, right? If it's multiplication, you got to use the product rule, right? You got to use the product rule. So in order for us to find y prime, we need to find the derivative of the first function, multiply that with the second function, and then add the derivative of the second function multiplied with the first function. I know I don't have a nice rhyme to go with this one, but hopefully you guys will remember that the product rule is in play here. Derivative of the first function, you can't even see that. That's terrible. So let's make it a little bit neater. here. It's derivative of the first function times the second function plus the derivative of the second function times the first. Identify those functions for yourselves just to make your life a little bit easier. X squared is going to be my first function. Sine of x is going to be my second function. So when I do this derivative, right, I make sure I take that into account. So y prime is going to equal to the derivative of the first function, which is 2x, right, because x squared, derivative of that is 2x, times the second function, which is sine of x, plus the derivative of the second function, derivative of sine x is cosine x, and times that with the first function, which is x squared. And if you want to, you can clean this up. You don't have to, but if you want to, and you want to simplify it, because you might be looking at a multiple, you can simplify it simply by rewriting this as 2x sine x plus x squared cosine x. And that's simplified, by the way. That's as most as you can do with that. And that's your answer, right? And that's your answer. Okay, so yeah, that's pretty much the gist of it. Once you have your trig functions, you can combine them with your other derivative shortcuts, and it'll give you your answer. All right, it'll give you your answer. Hopefully you guys still have the pair deck open. I want you guys to try one right now on your pair deck, and it's this guy right here. If you guys could give this one a shot. I'm gonna move this up a little bit right there so I can see that a little bit better. And then there's also a second one if you feel like the first one is too easy. I'm going to go ahead and unlock student pace so then you guys can go through and answer these ones on the pair deck. So if you guys could, oh shoot, I might have kicked you off the second page. So, so the slides are open now, so you can click to the next slide on there if you're looking at it. Yeah, if you guys are looking at the presentation mode of this thing. So what I just did was put it onto student guided, so you guys are student paced, so you guys can move the slides to whatever slide you need to go to. So if you guys want, you have to click it yourself. So go to slide 2, and you can go ahead and type your answer into here for me, or write it out into here. So I got 2 problems I want you to try. First problem is f of x is equal to 2x to the 5th cosine of x. I want you to find the derivative of this. And then for number 2, I also want you to find the derivative of this one, but I'm going to call it dy dx. I'm going to call it dy dx. Okay. And yeah, go ahead and do that. Let me go ahead and set a timer for 2 problems, product rule and quotient rule. Let's go with I don't think you guys need it, but we'll go 4.5 minutes. Yeah, 4.5 minutes. A 4.5 minute timer. Let's go with that. And then I'll see where you guys are after 4.5 minutes. So give it a try, give it a shot, give it a go. There you go. Let's see, so far for number 2, I got 16 responses. Not bad. Now be careful for some of you guys. Remember what I just said. Don't be tempted to just use the power rule of each of those functions, right? Look at number 1. Number 1, I'm telling you, those are 2 functions being multiplied together. That's not 2x to the 5th plus cosine of x. That's 2x to the 5th times cosine of x. And since it's 2 functions multiplying with each other, please make sure you use the correct rule that helps you to calculate that derivative, right? It's not going to be 10x times negative cosine of x, right? You actually have to apply. It looks like good. Majority of you guys are applying it. Some of you guys are not being too careful with it. So you got to go back and double check it. Can you send the pair deck link? Of course I can send the pair deck link. Give me 1 second. Oh God, too many things going off at once. There we go. Frankie, here you go. That should be the pair deck link, hopefully to get you in there. And yeah, let's go into it. Why does it say that there's still 9 of you guys still on the first slide? Is it just a little laggy? Maybe it's a little laggy. But let's go ahead and take a look here. I'm going to move this over just a little bit so I have myself a little bit more space. And we can work this problem out. Okay? Let's go ahead and go into it. This is what I want you to understand, guys. Don't look at this as one whole function, even though you're saying, knock me. It clearly says right there, f of x is this one whole function. I'll say, just be careful with that, right? This function is actually a buildup of multiple functions being multiplied together, right? It has 2 functions multiplied together here. It has the first function of 2x to the 5th, and it has a second function of cosine of x. Okay? I know some of you guys are like, but that's just one whole term. And yes, I agree with you. It is one whole term if you're working on it and you're just doing anything else. But when you're calculating derivatives, it is very important that you identify those functions and see how they're composed, right? See how are they built together, right? This is, if you actually write this out, this is actually 2x to the 5th times cosine of x. And why is that important? Back in the last section, it's when you take the derivative of something where it has something times something else, there's rules that are applied. And if it's just a coefficient, then the coefficient rule is super easy to deal with. You just multiply with the coefficient. But if it's a function times another function, you better use the product rule. You better use the product rule, okay? You better use the product rule. And that's going to be this one right here. So the derivative of f of x is going to be equal to the derivative of the first, which is going to be 10, because I bring down that 5, times it by the 2, is going to be 10x to the 4th, times the second, plus the derivative of the second. Derivative of cosine, we just found out, is negative sine, times the first. That is the derivative. Please, 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 you double check and make sure that you understand that that is the product rule being applied. That is the product rule being applied. And you end up here with 10x to the 4th cosine of x minus 2x to the 5th sine of x. Now, you could just leave it in this first line, and I'll be very, very happy if you do. But if you're looking at a multiple choice test, this is probably how the answer will be written. But if it's a free response question, like the ones where you're doing on my test and you're just writing it down, you can stop there. As long as you show it to me that you understood this is the product rule and you applied the product rule correctly, that's all that really matters to me. I don't really care about the simplifying part. If it's multiple choice, though, just understand that that answer might not show up like that. It might show up like this one on down here. Just read the directions and make sure you pay attention to it. Is it a one where they want you to simplify, or if it's just something that asks you to find it, you can just leave it there. Okay, so that's it for the first one. Hopefully you guys were able to figure that out and get that on there. We're gonna go ahead and move on to the second one. The second one, right, is a little bit easier to see as in terms of what type of operation is being done here, right? This one you saw that it was something times something. You might not have seen it though, but it is something times something. Hopefully you can see for number 2, this is something divided by something, right? This right here, we're going to be using the quotient rule, right? You're going to be using the quotient rule. You need the quotient rule for this one because it's a function dividing another function. Quotient rule comes into play, right? And if you guys remember from yesterday, the quotient rule is actually kind of fun to write out, right? It's kind of fun to write out. Call this cosine of x the high function. Call this 1 minus sine x the low function. And we just go ahead and multiply this guy out, all right? So let's go ahead and do that by using low d high minus high d low over low low, right? The quotient rule is low d high minus high d low over low low. And again, if you, I don't think you need to write that out. You're just going to hear that from now on, right? Low d high minus high d low over low low. Low is this bottom function. D high, derivative of the high function, is negative cosine x. Why did I write it so small? Negative cosine of x minus high, which is cosine of x, d low. And this is the part that trips up some students here. The derivative of 1 is just 0. The derivative of negative sine is going to come out to be negative cosine of x, right? It's technically 0 minus cosine, but I'm simplifying it out as I do that. And in the bottom here, it's low low, which is just whatever I have in the bottom written twice. That's why we say it as low low. So it's low d high minus high low over low low. I should not have written it that way, by the way. This is that's horrible notation. I shouldn't say y equals to this. That's terrible. It's y prime is equal to this. Whoops. I should never write that that's equal to the derivative. That doesn't make sense. A function cannot equal to its derivative. The derivative of cosine x is negative cosine x. No, it is not. The derivative of cosine x. Whoops. Did I mess up somewhere? Oh, I did mess up somewhere. Low d high. Whoops. That's what I was erasing. It's it's negative sine x. Thank you, Monica. Thank you for catching that. Low d high. D high, derivative of the high. Derivative of cosine is negative sine x. Good catch. Good catch. Thank you, Brian. Thank you. That's awesome. You guys are noticing and paying attention. I appreciate that you're catching that. So let's keep going. All right, we're going to go ahead and distribute this right here. This negative sine x is going to get distributed to the 1 and the negative sine. So I'm going to have here negative sine x plus, because negative times a negative becomes a positive, sine squared x. Sine squared x. Sine squared, not sine x squared, right? Sine squared x, right? The sine function is being squared, not the x itself, right? And then multiply this guy over here. I'm going to end up with negative cosine times negative cosine, which is going to give me a positive cosine squared x. And this is all, of course, over 1 minus sine x squared. Again, if you're doing this on a free response question, I'm happy here. I'm happy here. This is perfectly fine as long as you got every single term correctly, just like how Monica and Brian caught it right here. As long as everything's correct on the function and its derivatives, you get the full points right there. If you're taking a multiple choice problem, though, right, I guarantee you that probably won't be there as the answer. Instead, it will be simplified all the way through. And this is, you'll probably say, isn't this simplified then? And it's just a little simple extra step of distributing. And I'll actually let you know that is not as simplified as this can get. If you want to go further, you can simplify this even further. And it takes a little bit of, again, how much do you remember from pre-calc or your trig functions from pre-calc? This right here, sine squared x plus cosine squared x, we call that a trig identity back when you learned this in either pre-calc or IM3, right? And I'll put this on the side note right here, right? My side note is this. Sine squared x plus cosine squared x is actually equal to 1. That's actually the Pythagorean Trig identity, I believe is what it's called. I don't know if that looks familiar at all, or if it doesn't look familiar at all. This is something, it's a trig function that does show up quite often, and it's something that you need to know, that sine squared plus cosine squared is equal to 1. So I can replace this guy right here with a 1, right, and rewrite this as 1 minus sine x in the top, and in the bottom, 1 minus sine x squared, which, by the way, simplifies out to 1 over 1 minus sine x. You see how much it differs from the simplified version to the unsimplified version? They look almost nothing alike, but they actually are equal to each other. If I graph this guy up top with this guy in the bottom, it'll be the exact same graph. And that, that's just trippy to me, but that's what it simplifies out to, is 1 over 1 minus sine of x. Okay. Hopefully you guys are okay with that. Does that feel all right? Have I lost any of you on these two problems? Hopefully I haven't. Hopefully you can see all those examples with it zoomed out a little bit so I can give you guys a chance to copy it down if you haven't done so already. Yes, but it's okay. Yeah, it's not it doesn't feel great. But when you actually start working these through, you're going to realize, like, you know what? Calculus is actually kind of easy. I know that sounds weird to say, especially when you look at a problem, you're like, that doesn't look easy at all. But that's the people who don't know what it is that you're doing. Right? You don't actually care about the nonsense or the crazy messiness of those variables and those functions. You just follow the rules, right? And we have proofs of why these rules work. But now that we have those proofs, we can just apply these rules to see what we need to find, right? And if they give us some function and they ask us to find the derivative of that, we just do the rules of either the quotient rule, product rule, all those rules in there. And then we also remember that the derivative of those specific trig functions like sine and cosine, right? Sine and cosine. And with that, you should be able to find out what the general answer is, right? And that's what we really care about, just getting that answer right there. The non-simplified one, right? If it's, again, this is why I don't know why students like multiple choice answers, but multiple choice answers are I think like the devil. They like to do things and rewrite things, and it makes it harder to find. Whereas a free response question, you can easily get full credit for it without having to do all of the simplification of it, right? As long as you know what it is you're looking for, you can get the full credit on that. But yeah, that being said, those are only two of the trig functions that I was able to cover, which was sine of x and cosine of x. And for those of you who are still familiar or still remember, there are a total of 6 trig functions, and I'm going to try to get through 14 minutes. I'm going to try to get through all of them today. So let's go to the next trig function. Actually, here are the rest of the trig functions that we deal with. Tangent of x is the third basic trig function. So it goes sine, cosine, tangent, right? Sine, cosine, tangent. And then the last 3 are the a little bit more advanced ones, which are secant, cosecant, and cotangent. And I'm not going to prove those ones for you guys, but I will prove, or not prove, but I'll show you tangent really quick, what its derivative is and how to get it if you don't memorize it. Okay, so first things first, if you look at tangent of x, right, and you break it down, tangent of x is actually, if you look at it closely, it's simply just 2 functions combined together, 2 trig functions combined together. Tangent, actually, it's in its identity, you could rewrite as sine of x over cosine of x, right? One function divided by another function. And this looks messy, but this is how I used to do it. I never memorized the derivative of tangent, which is a terrible idea, by the way. You should memorize it. It's actually easier to do. But you could actually derive the derivative of tangent using the quotient rule, because you know what the derivative of sine is, you know what the derivative of cosine is, and you can clearly see that it's a function being divided by another function. You can use the quotient rule to do this, right? And I'll show you real quick. Y prime, right, would just be low d high. So in this case, low is cosine of x, d high, which is derivative of sine, which is cosine of x again, minus high, which is sine of x, d low, derivative of the low is negative sine x, all over low, which is cosine x squared, right? And I can go ahead and distribute this out in the numerator, and I have here is going to be cosine squared x plus sine squared x all over cosine squared x. And if you look at the top here, just like we did earlier, sine squared x plus cosine squared x is just equal to 1. And you end up with y prime is equal to 1 over cosine squared x. And that's what the derivative of tangent is. That's what the derivative of tangent is. But 1 over cosine is actually the same thing as secant. 1 over cosine is what we define secant to be. So this is actually the same thing as secant squared x. I'm going to write that off on the bottom right here. If you're looking for secant x, that's just the same thing as 1 over cosine of x. So therefore, the derivative of tangent, by the way, the derivative of tangent, I would write this down. And again, if you're making flashcards to help memorize these, the derivative of tangent is secant squared x. And that's all you could memorize. You don't need to derive it like how I did it. I literally used to do these 3 steps during the test just because I never memorized the derivative of tangent. I just remember from pre-calc that tangent is equal to sine over cosine. I did this extra work for no good reason, other than the fact that it's just like I don't want to memorize more things because that just seems like more work. I know that sounds counterintuitive, but that's just, young knocked me. He was weird. He tried to do things differently, but I don't know why he did that. It would have been easier if I just memorized the derivative of tangent is secant squared x. But I'm just saying, if you don't want to memorize it, you always can derive it, right? All right. That being said, next trig function that we're dealing with is secant. Again, if you know that secant is the same thing as 1 over cosine, right, you could, hear me out, you could derive the derivative of this using the quotient rule again. The high function in this case is 1, the low function in this case is cosine, and you could write out the derivative as a quotient rule. Low, which is cosine of x, d high, the derivative of 1 is 0, minus high, d low, all over low. And again, this isn't wrong. The derivative of secant is this monstrosity of a thing, but if you simplify this out, right, this actually simplifies out a little bit better here. This is going to come out to be, I believe, that goes to 0. Negative 1 times negative sine is going to be positive sine of x over cosine squared of x. And again, that looks like it's simplified enough, but you could actually simplify this further. Y prime could be written as sine x over cosine x times 1 over cosine x. And that simplifies out to, you ready for this? Sine x over cosine x, you can simplify and combine that as tangent of x. 1 over cosine of x, we just defined that, right? 1 over cosine of x is secant x. So what's the derivative of secant x? Again, if you don't want to go through that process of building this derivative using the quotient rule, you can just memorize it. The derivative of secant x is tangent x secant x. Whoops. Tangent x secant x. Right? Derivative of secant x is tangent x secant x. Right? Tangent x secant x. And that's just another one that you could just memorize as well. In fact, by the end of, I'd say, either next week or the following week, you should know the derivative of any of these 6 trig functions by heart. So if I ask you what's the derivative of sine, you need to be able to tell me that's cosine. What's the derivative of cosine? You need to be able to tell me that it is negative sine, and so on and so forth for all 6 trig functions. So far, I've only shown you 4. I showed you tangent, and I've showed you this next one, which is secant, and I'm going to show you the rest of them right now. Okay, I'm going to show you the rest of them right now. Let's go with the derivative. Wait, why is that written twice? What? Ignore that one. So we got that one right there. Y is equal to secant, and then the other 2 is going to be y is equal to cosecant and y is equal to cotangent. Right? Y is equal to cosecant and y is equal to cotangent. And again, you don't have to do it this way. You can just memorize it, but let me show you where these guys come from. And it also helps to see like what is cosecant the same as, right? So hopefully you understand that secant itself is 1 over cosine. Cosecant is the same thing as 1 over sine. And again, you could just use the quotient rule for this, right? And just calculate the derivative of this one using the quotient rule. Low is sine x. D high, derivative of 1 is 0. Minus high, That's not a minus sign, knock me. Minus high d low all over low sine squared x, right? You don't have to do this, but again, I'm going to tell you, you can do this just if you don't want to memorize it. And it's a little bit of practice on your quotient rule. So you end up with negative cosine of x over sine squared x. And just like the trick I did earlier, I can split this up. Y prime is going to be equal to negative cosine x sine x times 1 over sine x. Well, here's the deal. 1 over sine x is just the same thing as cosecant x, right? That's an easy replace. But this right here is different, right? Sine of x over cosine of x is tangent. If you flip it, you end up with 1 over tangent, or in other words, cotangent. So cosine over sine is actually the other one. It's not tangent, but instead it is cotangent of x. And of course, don't forget the negative sign that's in front there. So y prime of cosecant is going to be negative cotangent x cosecant x. Whew. Okay, so that's that. That's another one that you need to memorize, right? And then the last one is cotangent. And cotangent, I'm hoping you can see, same thing applies for this one, just like I did for tangent. I hope you can see that. Cotangent is going to be the same thing as cosine of x over sine, because tangent itself is sine over cosine. Cotangent flips that value for you. And you could do the same thing. You could calculate this out by using the quotient rule. And I'm going to just write this out real quick. Low d high, derivative of cosine is negative sine x, minus high d low, derivative of sine is cosine again, all over low sine x squared. And if you write this out and simplify and multiply, you end up with negative sine x squared minus cosine x squared all over sine x squared. And this right here, if you factor out a negative sign, it's going to be the same thing as negative 1 times sine squared x plus cosine squared x. And the reason why I factor out that negative 1 is because this right here, right, sine squared plus cosine squared is the identity for 1. So when you go further along here, this y prime is going to be equal to negative 1 over sine squared x, which just simplifies as to 1 over sine is the same thing as cosecant. So there's going to be negative cosecant squared x. And that's what the derivative, and that's the only one I really care about you memorizing, is that value right there. So there's 6 trig functions in total that I need you to memorize, and I need you to know and to have those derivatives down. And then you're going to be combining this with what we learned in the last section, right? Using the product rule, quotient rule, addition and subtraction rule. All those rules apply with these trig functions as well. Okay? So when you are doing your next set of homework problems, which I should post by the end of today, if I don't post by the end of today, just stop by my office hours to remind me or send me a reminder. So you can start working on these practice problems, but I will post them on there, and you need to practice these out, right? I don't care about the simplifying part, but I do care about the actual derivative part. So setting up the derivatives is very important to me here. So getting those down and getting these memorized will help you to do those problems. Why do I have written cotangent down here? So here's what I want you to do, right? So here's what I want you to do. Get these down on a flashcard somewhere, right? Along with their derivatives. So you write down the 6 main trig functions: sine x, cosine x, tangent x. And then the other one is secant x, cosecant x, and cotangent x. What I want from here is, if I were to go in here and take the derivative of all these, tell me what the derivatives are, and you need to know these by heart. Again, if you don't, you can spend like the couple minutes and derive them like I just did, or how I used to do. So taking the derivative of this, d dx, taking the derivative of this, I don't like my notation for this, So let's say I'm taking the derivative of this one. The derivative of sine x, you need to be able to tell me is cosine x. The derivative of cosine x, you need to tell me it is negative sine x. Derivative of tangent x, it is secant squared x. Derivative of secant x is equal to tangent x secant x. Derivative of cosecant x is going to be equal to negative cotangent x cosecant x. And the last one, derivative of cotangent x, is going to be equal to negative cosecant squared x. You need to get these 6 down. However you need to do it, make flashcards or practice, or do what I did and just memorize the first 2 and derive the rest of them by hand later on. I don't really care which way you do it. Honestly, though, just out of experience, memorizing these 6 is actually a little bit easier to do. Just having them known makes it easier, but it's not mandatory, right? As long as you know how to derive them, you're good to go. And that's going to be it for me today, guys. It's quite a bit, right? It's quite a bit. Hopefully it wasn't too much, though. Hopefully you guys are okay with it. Derivatives aren't that bad, right? Derivatives aren't that bad. And now we're just getting these shortcuts to do them so we don't have to use the limit definition of it, okay? All right, guys. That's it for me today. I'll put the homework up later today. If you have any questions, I'll be in my office hours today from 1 to 2 and tomorrow from 1 to 2. And that's going to be it. Have a good weekend. I won't see you until Monday. So stay out of trouble, stay out of jail, and don't get pregnant. All right? So long, guys. Have a good weekend. Farewell. Bye-bye. Bye, Monica. Bye, Relly. Bye.